So I am going to have to apologise. I may end up in a bit of a coughing fit occasionally because stupid people who gave me the lurgy, and my bloody family didn't get it, only I did, which is quite annoying. So who am I? Okay, press the on button works. Who am I? This is me when I was younger, thinner and more hirsute. Those are my socials. I work at PTP, where I do a hardware hacking, and I'm head of R&D. Not that that's exciting. My avatar is most commonly known because we got drunk one day and decided to burn a Furby, because why not? That is the highest resolution that 2008 will give you, by the way. So, what I really am not is I'm a totally serious person who will not find the name of the seventh planet in the solar system amusing. I will not find anything about that planet amusing at all. So, one of the reasons why I'm talking to you here is not, forgot this bit, I'm not the only one. One of the reasons why I'm doing this talk is people have seen me talk on various different things from security perspective. My last talk I was doing this year was on psychological stuff. But my actual degree is in planetary science and astronomy. I can't even say the name of my degree. It's space stuff is what my actual degree is in. And as the theme this year is space, I decided to actually go on a bit about how space communication works and how, amazing it can be. By the way, the time has gone to sleep. There we are, high technology here. So anyway, this is space, which I'm endlessly fascinated about. I'm going to quote the late, great Douglas Adams here, is space is big. You just won't believe how vastly, hugely, mind-boggling big it is. You might think it's a long way down the road to chemists, but that's peanuts compared to space. It's sort of mind-blowing how big it is. It's, and how many fascinating and interesting things you can find in there. As humans, we have probed our solar system quite definitely. We've been to every single one of the 8 planets, which are listed up here, and if you can remember the rhyme from your school, then, you can repeat it to yourself. We've been to dwarf planets like Pluto. We've been to a Kuiper Belt object, which is at the far end of the solar system, which is Akasor. No, getting the wrong name. It used to be called Ultima Thule. And then there's, I can't rename that one. It's the asteroid we landed Rosetta probe on. And we've been to moons like Callisto and Enceladus there. So it's absolutely amazing how far we've gone, what we've done from this tiny little gravity well where we're based. I'm going to get into the physics here a bit, because there is quite a bit of physics in this, and I do apologise. I will be asking questions later, so I hope you take notes. That's a bit of a joke. So, what is space? What is where we are? We live on this planet. We live on this planetary area. I'm sorry to say, the Earth is not flat. I can definitively say space exists, the Earth is not flat, and whatever conspiracy theories. Chemtrails don't exist. There we are. But we have many layers of atmosphere above us. We have troposphere, which is bounded by the ozone layer and the stratosphere. Normally, if you've got a weather balloon, which is the easiest way to see the curvature of the Earth, is you launch that up, that will go up to the stratosphere. Beyond that, we've got the mesosphere, and then there's a Kármán line. The Kármán line was decided by an American-Hungarian physicist called Kármán, that would be the rough border of it. It's set at 100 kilometers because it's a convenient number. That's all. And that's in the very start of the thermosphere, then we end into the exosphere. What will become later is bits of the mesosphere and the thermosphere and a tiny bit of the stratosphere, is called the ionosphere, which is basically a cloud of ionic particles which sort of surrounds and protects the Earth. Without that, we'd be dead. There wouldn't be us. We'd be like Mars, a dead, barren universe. Planet. Where satellites often live, in astronomical terms, is we're surrounded by these things called the Van Allen belts, which are basically radiation that is hit by as the solar panel. The solar wind hits our planetary atmosphere. It creates a load of radiation, which is what we call the Van Allen belts, and they're sort of like donuts. So we have low Earth orbit, where most satellites are, which is close to us. It's not particularly stable, and it requires quite a bit. Medium Earth orbit and geosynchronous orbit. Advantage about geosynchronous orbit is it's a 24-hour cycle, so basically it means the satellite can be directly above us. What does that look like? That is low Earth orbit. That's a satellite tracking website that you can use. It's public accessible, and you can see all of those. Most of those are Starlink, which is the sort of impact that Musk has had on the world so far. If we zoom out a bit, we can see, it's quite hard, but you can see the geostationary ones in this ring around, basically the poles, and up at the top you can sort of see the medium Earth orbits. So that's how our planet is surrounded. We've got loads and loads of satellites. To be honest, our modern life wouldn't work without it. I use GPS to get here. That's satellite driven. Some people are Starlink. Satellite phones allow people to get connectivity where you can't normally get it, where you can't have cells, can't have cables, etc. Satellites have revolutionized, have improved our lives. They're also brilliant for science, because we can do amazing things that I'll go into a bit later that we'll never have known about the universe without satellites. So how do we start? How do we get something from this gravity well into space? This here is an artist's rendition of the V2 rocket, which was a wartime rocket developed in 1942, I want to say. I might be wrong, I'm not a historian, by German scientists as a way of easily bombing Amsterdam and London and some of the northern bits. It had range. It was a bit flaky initially and would occasionally fall apart, but it did have an impact. Allegedly not much of an impact, because it cost way more than it actually did for the Germans. But it meant that there's a load of rocket scientists that the Germans had, which everybody wanted. So they pretty much, as soon as the US and Russia came in, they went, "We'll have you," and stole people abroad, across. There are lots and lots of programs that you can see about that. But that's how they start. Go on to rocketry. There is another problem with rocketry, and I'm going to get into an equation here, which is how do we get a payload in space? So payload is all about mass, and we have to achieve a certain amount of velocity to get it off this, overcome gravity, overcome air resistance and all that. And one of the problems with that is you have to account for fuel. And fuel weighs amount, so we have to work out how much fuel we need to get off, including the fuel that we need to get off the planet, which is what that equation is. That's the ideal rocket equation, and it basically goes on about how much mass you need. This is why getting stuff into space is expensive, because we need to have the fuel. In the old days, that rocket uses ethanol and oxygen mix. So basically it's powered by vodka, which I'd love to say I would as well, but I don't think you can get a rocket into space based on a pint of dog. Though several people I know would probably try. Nowadays we tend to use methalox or methane. So, SpaceX it started to move towards methalox, whereas it used to use methane and with an oxygen starter. I'm going really too fast now. So another thing that we need to do when we get into communication, we need to understand the electromagnetic spectrum. So this is something that covers everybody. I can see everybody who failed physics is going, no, because they can all remember that from school. It's a big thing that requires us allows us basic communication. This is used in normal communications and everything like that. It's gamma rays and X-rays are used in medical applications. We see things because of light, et cetera, et cetera. So but the problem is the atmosphere will block most of these. Pretty much except for visible light, infrared, ultraviolet, and radio waves, it will block most of that. So we can't use a lot of these things to carry messages. So this is roughly, we use something called modulation to try and do it. We have what's called a carrier wave, which is basically a standard frequency, that a standard basically way that we can modify together, and we can do that by a number of different methods. AM used to be old radios. I remember tuning to those. FM is sort of more modern ones, and digital is what we use, is a sort of mix of those. Anybody who remembers computers in the 80s and loading stuff from tapes? That's sort of, you'll use normal digital modulation to try and get the frequencies of it. I have talked about that in the past because I'm quite a geek for that. So to propagate stuff, because we can't run a cable everywhere, definitely can't launch a satellite 15,000 kilometers into space with a cable attached to the back of it. That really won't work. So there's a number of ways that we can propagate messages. So one thing is ionospheric bouncing, which is how we used to do this in basically in the satellite era, is you can bounce a message directly off the ionosphere, which I mentioned earlier. That was quite commonly used to get messages from like America to Europe, and it'll be on the curve of the Earth. There's the other thing that we can also use is a moon, because that's static. There is a 2.6 second delay, because it takes 1.3 seconds for light to reach the moon and 1.3 seconds for light to reach back again. That was successfully tested by, this is an American-US ship called the Moon Relay, which tried this as an experiment. It worked, but it's not that feasible. And nowadays we use basically, we can use satellite ones using, where's the term? My brain's not working. It's listed on it. We can use basically a bend on the satellite to allow a satellite to relay us a message. Also, because we can choose what satellite is, we don't have a problem with time on that one. That's sort of how satellite phones work. Right, I'm going to start you with a bit of history of space exploration. This is where we start to get into the techie bits. There we are. End of physics, okay? So, anybody recognize this? Sputnik 1, there were two Sputniks, Sputnik 1, Sputnik 2, which were basically the Russian winning the first step of the space race between the US and the USSR. So Sputnik went into orbit for 22 days, Sputnik 1, before it basically deorbited. That's a photo I took of, I can't remember where that is. That's from the Udall Hazy Center near Washington, D.C. I took that photo when I visited it many years back. I think that's a replica of the original Sputnik. So it's not very big. It really isn't that large. Anyway, this is roughly what the signals for the Sputnik look like. There was a lot of questions about how, I suddenly realized I forgot to bring my mouse, so I've got to try and do it. Give me a second. Right. So I'm now going to play, first off, I'm going to play two bits of sound samples, and I'm a bit worried that because I've not connected this to the internet, it might not work. The first one is possibly the greatest misuse of a voice actor ever from Civilization 4. Nope, it won't work because I'm not connected to the internet. No, I'm going to skip that. So basically, there's a sound sample of Leonard Nimoy, who plays Spock in Star Trek, going beep, 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 which is just total wasteful. And then we have a sound sample of the actual Sputnik communication, which is basically a beep. And it just repeats beep, 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 roughly every few seconds. And that just continues. That was the whole of the Sputnik signal. So, there is no data in it, which many people have tried analysing. Doesn't mean that people weren't worried about it. There have been papers that have been published about the transmission data. And this is a declassified document that came out in, I think it was the 80s. But it was obviously written beforehand, which basically looked into transmission to try and find any sort of data that could be found in that Sputnik signal, because there was total paranoia at the time. There we are. That's a basic statement, is what could it have monitored, what could it have sent? To be honest, not much. There wasn't much battery in the Sputnik. Even if it did, it couldn't send that much data. Anyway, I'm going to map a few I've used AI to generate me images, okay? It's terrible. I'm not a good artist. I'm going to map a few of the InfoSec concepts to the space and see how they get represented. So we'll start with everybody's favorite, confidentiality. So one of the problems with space travel is a lot of the technology was designed in the 50s, 60s, 70s, 80s, 90s. And I don't know how many of you remember how much encryption was in there. There's bugger all. It's like XOR encryption was all I remember. There was, sorry, I'll go to an example in a second. But there was a point where it was actually illegal at certain points to actually export encryption from the US. That was up till the early 2000s, I believe. 2001, yeah. Yeah. So let's have a quick look. But even still, it affects modern day. So SpaceX is, I'm not a big fan of Musk, but SpaceX is an amazing organization. It has revolutionized the way that we do space travel. It's taken it away from NASA, moved a lot towards commercial gain, and has actually changed how we do it. They've done reusability. It's actually quite amazing. That do not endorse Musk. I endorse SpaceX. It's not him. He's not the engineer. But until recently, they have a lot of telemetry feeds everywhere. So there's cameras and there's telemetry feeds from all their rockets. It is related to space travel. This is still a secret technically from US one, because it's all related to rocketry, and everything to do with rocketry is a US secret. So you wouldn't really want that to be private, would you? Sorry, public, would you? So you can, if you have an SDR, I was going to bring one as a prop, but I forgot it because my brain isn't working at the moment. You can buy SDRs for £100. They're not exactly expensive. And if you were roughly in the area, you could get the launch of it. You could read the telemetry. This is the frequency that it is on. There are plenty of places. This is root.cz, which has listed a load of these and decoded them. There is one thing. It's like don't annoy radio engineers because they're real geeks and they will reverse engineer everything. So you can see there that they've taken everything. I think I'm good at reverse engineering. I'm nothing compared to that. The amount of levels where they can just read a radio signal, work out the modulation, work out the bits that are everything. So we can actually then take the telemetry and actually get the images directly from the cameras, which is really nice. Fortunately, they now encrypt it. So this is a legacy demo. But this is quite common throughout. I've got a few more examples. That probably should have been early in my presentation. So this is an example of how encryption used to be a secret. This is from the late 90s. It's a t-shirt of 95. It's a t-shirt of the RSA encryption algorithm, and it was done as a protest against the US export regulations with cryptography. Anybody who tests TLS, this is why we have export level encryption ciphers, and we find them still every bloody where. POE satellite. So the POE satellite are meteorological satellites done by NOAA, which is the North Oceanic. It's written up there. But polar operational, everything becomes acronyms, and it really, my brain runs out. I've got so many acronyms stored, I will forget half of them. But the POES is basically, it monitors satellite details. It's a meteorological satellite. It looks for clouds. It looks for anything that looks weird on it. It's quite high level. You won't get like detailed photos of your house from it, but you'll get a photo of a country. I was going to do this as a relatively live demo, but you can see right at the top there, it was decommissioned in August. I started having a mess around with this at the first week in September. And it took me, it was going, why isn't this working? Why can't I pick up the signals? Oh, it's been decommissioned. That was there's no reason for decommissioning other than basically a certain, the US current leadership decided to decommission it. So it uses an analog method of transmission. So it will translate data and it will have an analog feed directly from the cameras on it, which you can pick up. You can pick it up with this equipment. So that's an SDR. That will cost you about £100. You can make that yourself from a couple of bits of bent coat hanger and a chop box and a bit of coax. And that is a signal amplifier. You don't necessarily need one for pose, but for other satellite ones you do. This is essentially how to pick stuff up from satellites. That is generally your equipment. This is roughly what it sounds like. I was going to play a sample of the wave. It's a bit like, it's sort of like a few beeps, but you have occasional sort of sound like an old tape player from the 1980s if you play games, or a modem if you remember those. I'm starting to realise some of the people in the audience won't have done modems or tapes, and now I'm going to start feeling really old. So anyway, this can be downloaded. There's a program called SatDump. It's totally open source, free to do. We'll do a load of different satellites. As I said, I couldn't find one because they decommissioned the sodding satellites. I spent ages waiting for one to pass over my house, and then it's like, oh, it's been decommissioned. So I did the cheat method, and I downloaded a pre-made WAV file that somebody else had downloaded, had sniffed from it. So it's a relatively simple program. It does all the thinking for me, which I like in programs. I like things to do my thinking. So this is the general output. You've got multiple different images. This is in different levels. You can see the UK there. You can see Iceland there. You can't see Scandinavia. So this is visible light. This is infrared. So it allows you to see a number of things. You can see the clouds. You can see the penetration to the clouds. You can see the rough heat level. So it's perfect for meteorologists. I'm not a meteorologist, so somebody who's meteorological can understand this. There are other sensor streams on there, but yeah, they're not visually appealing. Sorry. Right, integrity. So we all know integrity is reading stuff. So this is, sorry. I've just realised I don't have my notes and my brain is, as I said, is going. I've lost my cursor. It doesn't matter. Right, so that is one of the satellites in medium Earth orbit. Sorry, I can't remember the name. Don't have lurgy before you do your talk. You forget the basic things. So that is a communications relay satellite. So that will relay communications, and it's used by the US military to relay communications between various parts of the different Americas. It basically is just a nice relay. It's great. Everything's encrypted because it's military encryption. The actual messages aren't encrypted, but the contents of the messages are. So it's everything that we normally expect. TLS, fully protected. There's no real way of abusing that, is there? Except it relays. It doesn't check who's sending the messages. So when you've got a load of Brazilian radio pirates who decide that they want to pass on, where should we drop our drugs? It's a perfect thing to bounce off. So, and the problem is, because it's relatively short, your power in the equipment isn't that much, so you can move it. Someone wants to track you, they can't. So, it's the old thing. There's no checking of integrity, there's no checking of who's doing that relay. And let's go quickly on to availability. This is a tiny bit of integrity in it as well, but I couldn't quite do it. Example I used to get here today is something called GNSS, which is the whole global navigational satellite services, which cover GPS, which is the first one, GLONASS, Baidu, Galileo, QZSS, IRNSS. So those are all the different ones that you can do. There's loads of them. Most times your phone will use GPS, GLONASS, and Galileo. But there are alternatives like Baidu. How does it actually work? I actually asked my eldest one on a car journey once. It was a very boring car journey. And he was going on about, well, you send a message to satellite and the satellite works out where you are and sends it back. And it's like, that's not really feasible, is it? So you've got these satellites and they've been there since 1978. Your GPS transmitters, you can get a GPS module that's like that big. It's not got much of an aerial. It's not got any power at all. You can fit it in a phone. It drains your phone, but it doesn't drain it that much. You've got to physically power it somehow. It can't really be an active transmission medium because you just don't have enough power. It's got to be totally passive. So the easiest way, and it's defined in, there's a number of different IS-GPS specifications which are all public. This is 800, which is the L1C, which is the frequency one of the frequency it uses. The 200 is the actual basic one. And that defines what it does. And basically, it sends a timestamp. And then it can use that timestamp to actually work out where you are. So here's roughly what it uses. It's got a navigational message. It's got what's called a CA code. That's your civilian one rather than the protected code, which is slightly more complicated, and that was used by the US military and is encrypted. And you got the carrier wave. And remember where we did carriers all the way back there. So that's just standard frequency. They get XORed together and they get sent out, so you can then de-XOR them, and it's relatively quick to do. So there's two bits of important information here, the navigation message and the CA code. So this is your CA, and it's a frame divided into subframes and pages and bits. So the important bits are your, press the wrong button. You have, my laser stopped working, there we are. We have a clock, which is your clock feed, and the clock's quite funky, and I'll go into that a bit later because it's a very weird way of doing a clock. You have your, I can't even say that, that's a bugger. So that is an old school term for when people used to do astronomy and they used to look at telescopes and they used to go, this is where Pluto will be, or this is where Jupiter will be, and it used to be a paper almanac. And this basically says where the satellite is. It lasts for about 4 hours, that word. And what you'll get later is you'll also get part of something called the almanac, which is basically 2 weeks of where that satellite is. So your receiver can go, here's a satellite 1, I've just got a signal from that there, satellite 2, satellite 3, munge them together, triangulate, do a bit of maths on the actual receiver, and the receiver works out where you are. That's why in the old days, if you remember old like TomToms and so on, it would say, right, collecting satellites, it'll give you 3, 4, and then you can see your actual, your accuracy get further. So going back to it, this CA code I've just remembered is called a PRN. I don't know what it is. I couldn't be bothered to Google it. I just had too much of acronyms at that point. The PRN is a unique number. It's a 1023-bit message that is repeated regularly, and basically it covers one bit of that is 293 meters of distance from the satellite to you. So we are talking highly exact numbers, because that's basically sent every 1 millisecond. So if you're out by a millisecond, every microsecond, if you're out by a microsecond, it covers 293 meters. That's quite a bit of accuracy that you need to account for. So we have what's called time that we need to work out. So who knows what time is? I mean, my time says 10:11, but it's British summertime. That says I've got 11 minutes left. I know. That's British summertime. That's the time zone, and that's an arbitrary time zone that we decided to have. Time in the US is whatever it is currently plus minus 5. So, but we can't do that when we're doing exact, literally to the microsecond times. We need to have we have something called GPS time. And GPS time is based on UTC, which is Greenwich Mean Time, basically. And it's done in a weird way. You have bits for weeks, and you have bits for, number of 1.5 second periods within that week. So it's a bit strange. It all goes from, an epoch of 1980, I think it's 6th of January 1980, midnight. And then it's number of 1.5 second counts until the end of the week, and then the week rolls over. And it goes on to the next week, which is all fun. GPS time, one of the problems is because we're so exact as well, we have to account for relativity in this. So you're at the point where the actual calculations you do need to account for relativity. In this one, it defines the speed of light in the actual standard. That is actually the speed of light. The speed of light is defined nowadays. It used to be defined in terms of counts of meters, but now meters are actually defined in terms of the speed of light, and the second is defined in terms of the speed of light. It's one of those universal constants that doesn't change. That is guaranteed to be correct. It is the right value. All us old people, we remember the Millennium Bug. I remember working that night. I remember all the setup. So the Millennium Bug, for those in the younger ones, I'm assuming that some people might not remember it or think it was a myth, was in the old days, people would use a 2-digit field for year. So and they'd add 19 to the front. And then came to the 20th century and suddenly everybody went, oh yeah, that'll get confusing. Everything would suddenly drop 100 years in the past. So a lot of money was spent to make sure this didn't happen. I remember doing testing for it. I remember actually working that night. Instead of getting drunk like all my mates, it was quite annoying. But yeah, it's a big thing. It's known now as a sort of the class of bugs when you have date rollovers. People have heard of the 2038 bug in Unix, which is when the 32-bit time T rolls over, which hopefully we shouldn't have because it should be 64-bit by then. GPS has that. This is the standard for transmission week number. I mean, you can see how complex standard is by how many bloody subsections there are in that. I'm going to just highlight words. So 10 bits, 10 LSBs. So anybody who's used to binary, how large a number can you get in 10 bits? Yeah, 1024. So 1024, and remember we're counting weeks from 1980. 1024 divided by 52 is 19.7. So every 19.7 years we will reach an epoch, and we'll have a problem. Last one, 20, was April 2019. There were impacts. It wasn't totally one. Apple had to push an emergency patch to iOS to make sure that nothing happened. Fortunately, people realized it. There were a lot of problems with, like, parking machines failed. So you got to pay your parking, it would go, oh, yeah. Because, of course, everything gets a fee from GPS for time. Next one, that's a different one, sorry. Next one is 2038. But not April, which is when the Unix one is, it'd be November, so I'm planning to retire by then. Or maybe go into contracting and get some money, I don't know. So next impact is so that's availability problems. The next one is whilst we're on GPS, I'm going to go into GPS spoofing and jamming. So this is my colleagues who do aviation stuff who've written about GPS spoofing on aviation safety. This is quite big at the moment. I've seen news articles about this. Quite often it's affecting, this was like, a couple of days ago, it's affecting like defense ministers going over Russia, parts of Eastern Europe, parts of the Middle East. There is active spoofing and jamming. Spoofing is easy. You know what the carrier wave is. There are anti-spoofing protections in GPS, but they're in only certain streams. Jamming is easy. It's really easy to jam radio waves. You just broadcast lots of radio. And you just fill the spectrum. It's really easy. There is an active map, gpswise.aero, which will show you active real-time spoofing and jamming. So it takes the ADS-B data and maps it to where the plane really is. And what their flight path is. And as you can see, there's a whole load here over Eastern Europe, and there's a whole load down over the Middle East. It's quite a serious problem that's having quite an impact. So we'll move on from, this is, if you might have noticed, the aliens changed because I ran out of my credits on ChatGPT, so I had to go to Gemini. It did a good job at trying to replicate it, but, there's some subtle differences. So we've got CIA, and then how do we fix stuff? So the next one is patching, because everybody has stuff they need patch on. I'm a pen tester in my day job. I constantly report on things out of date, things that need patching, outdated libraries. There's nothing new about space. The first and furthest IT remote call so far from a human call, That's Alan Shepard on the moon. And again, the moon landings did happen. So there was a fault code from the lander as it was released from the command module was released. So the Apollo one had different modules. It had a command module which actually landed on the moon, and that got released from the actual bit that orbited the moon where one astronaut would stay. There were fault codes that came from that as soon as that got released from the main one, and it was assumed to be a dodgy solder joint. So they actually got Alan Shepard to go and put his finger on various different bits to see when the code where the dodgy solder joint was, and then they sent him a literal patch that he could actually key in by hand to just ignore that feeling and suppress the error codes. Voyager 1, I don't know whether you saw this in 2024, it stopped responding. And absolutely amazing, they sent a patch. Voyager 1 is at the far end of the solar system. It's practically left the solar system now. It is 23 light hours away. So that means if you send a message to it, 23 hours there, 23 hours back. 46 hours between each response. It's not, you can't get a SSH terminal through that. But it's patched. It was absolutely amazing. Whoever did that is a genius. The thing is though, all Voyager was done long ago that all its data is public. So your telecommunications are public, your actual software are public, you can find a stack of actual, the original source code for it, if you look hard enough. In theory, you can do it yourself. Except for you need a really stupidly powerful telescope. This is one of the sites of NASA's DSN, Deep Space Network. So yeah, good luck on that one. Nowadays we have CubeSats, which are built basically, they're open source satellites that you just plug boards in. Think of them as Raspberry Pis in space. And I designed one of these as part of my degree, and it was basically, they don't care about the security, they don't care about the backbone, they just want to plug all their boards in, and run that. So they're all based on open source stuff, so there's obviously patches for that. Perseverance is a rover, and it had the first helicopter to fly on a foreign planet on Mars. I know I'm running short on time, I'm just gonna say, how freaking amazing is that? You had a helicopter fly on Mars. That should astound everybody in the room. That is based on open source. There was a badge released by GitHub of all the projects that it used, and I apologize for the colour. Let's zoom in a bit. So, Log4j has something known as Log4Shell. There is a remote code execution vulnerability on a helicopter on Mars. Space telescopes, I've only got this in because this is in the title of my talk. Space telescopes were absolutely friggin' amazing. You can see everything. This is gamma rays. This is looking at a pulsar that is billions of parsecs away. A pulsar is basically a neutron star that sends out magnetic. It spins around really fast and sends out pulses of data that are absolutely brilliant. This is X-ray. This is the stuff we get as one. This is from the James Webb Space Telescope. That is an exoplanet. So this is a planet in TW7, which is quite a few light years away. We can see other planets around other stars now. That is so amazing. This is all communicated with, called NASA's JPL's Deep Space Network, which is based in California, Madrid, and Australia. So it can always communicate and goes and downloads links, everything. This is public information, you can see there. Somebody has done a paper on exploring the security. I got really excited and read it, and it's basically it's a documentation review. That basically goes, oh yeah, somebody could break in. But though we did have interest in one is carries a Korean space team. So they transfer data to everybody, and each one is individual and different. So it's amazing how it is. So there are potential risks there. Need somebody to look into it, but it's a normal risk you get on a location. The future. Space is big. It's growing. You've got SpaceX, Blue Origin, and the UK Space Trade Association. I just put those in just to have something UKE. There are plans for looking at Cornwall, Isle of Man, to try and do space industries. It's an active thing in the world. That's the physical side of a nanostat. It weighs 2 kilograms. Price to launch 2 kilograms at the moment is about $1,000. And it will get down to about 20, and I've run out of time, so I've got 2 minutes. Right, so so in theory, everybody in this room could launch a satellite. It's within individual cost. It's a bit more than that because there'll be agreements with SpaceX. This leads us to the next problem, which is space junk. That is a current space junk tracker. See that red bit? That's mostly SpaceLink's, the Starlink stuff deorbiting. It's fine if it deorbits, it will burn up in the atmosphere, but if it doesn't, that's all stuff whizzing around that can hit somebody at vast relativity speeds. And that's it, basically. Sorry about that. So, yeah, any questions? Oh, I can't use a question ball. We've got the mic ball here. This is great. Somebody ask a question just because I want to throw it. Nope. Okay. I've obviously stood bored. There you are.
I just wanted the ball.
Okay. There is actually a question at the back there. Do you want to pass?
Has anybody hacked satellites?
DEFCON had the NASA, it was either NASA or Department of Defense had a Hack the Sat competition in DEFCON for the past couple of years. It has in theory been done, as in there was exploits there. Nobody's done it in real life. You wouldn't do it by launching a space shuttle and doing it like you do in the films. You would do other methods. Ooh. Anybody else? Oh, I'm going to have to go quite loopy. So somebody catch and throw. Oh, nearly. Everybody's too embarrassed to throw the ball.
You talked about, hello. You talked about piracy affecting satellites. How does that differ with mid-Earth orbit and geo-Earth orbit, or the GEO one, sorry?
Geosynchronous, it's a lot more power to actually reach. So yeah, it's likely you would need bigger locations so you'd be easier to track you, basically. Ball coming at the head! There's meant to be a relay of helpers, and they've all decided to hide. Anybody else? And I think that's it then. Oh.
Very frivolous one.
Hold on.
I'll just shout. Testing. You said you could launch your own space satellite. What could you do with it? Could you just be broadcasting an image or something like that?
Launch a satellite, whatever you want.
I was thinking you could do goatsy in space just for shits and giggles.
Literally, yeah. Most of them will be like scientific information.
Yeah.
So stuff you can get from, outside the atmosphere, because the atmosphere is quite restrictive what you can get through.
How would people find it? Do you just have to give them sort of coordinates or something like that, or is it just broadcast?
You don't need much power to get up that far. I mean, look at your GPS receiver. So it's whatever you define.
Awesome.
So,
Ready?
Right, I think that's it.